All right, let's go ahead and get started today. We are going to jump around a whole bunch about assembly today in hopes that this will make some sense, yes.
What chapter is K-Maps in the book?
It is not in your architecture book, it is in the optional book.
I'm pretty
So
sure
if you bought the optional book, it'll help you there. Otherwise, Google.
Yeah.
If you don't have the book, I have it. I'm pretty sure.
So today I'm going to try and get through all the assembly language because your lab is with assembly. And we're basically just going to do a couple of assembly instructions. Again, hopefully it's been, you understand why we have assembly because it's how we actually program the machines. But assembly level programming is actually writing somewhat English-like statements, or at least abbreviations, for the machine instructions. So you'd actually write add these two registers and then be able to code it from there. You know what, let's look at an example because that always helps me. So I have uploaded an assembly directory up on GitHub, and I put 7 example assembly files along with a template. And I'm just going to look at the first assembly, and we'll just poke through that first and then go through more of the theory afterwards. Hopefully it'll make a little more sense. So this is doing, wait, we did this last time with the add?
Did we?
Yes.
Yeah, we did this.
Okay.
I remember that
Maybe
file.
everyone was tired? All right, we'll do it again.
Hey, but I remember it.
Okay.
That's important.
Exactly.
I highly recommend for MIPS assembly, keep in mind that assemblers are different per architecture. We are studying MIPS, which is not what your machines use, but we're studying MIPS because it's way simpler than x86. But to go from MIPS to x86 is actually not that big of a jump. The big jump is just learning what assembly is. So up top is where you'd have your data segment. This is if you're trying to declare any global arrays or strings or messages. In this program, it's just going to add 10 and 11 and put the result into register 10. So we don't need to do anything constant. Next comes your text, and that is where your code is. Text is code inside of assembly. Global main, that's just to tell the assembler, all right, this is your main function, and the assembler just knows that when it loads your program to start executing the first instruction that's inside of main, just by convention. Main is the label, so that's the first label depicting where main is. And the first instruction is going to be OR I 8, register 8, 0, and 0xa, which is 10. ORing immediate, so if you take 0 and you OR it with 10, what do you get back? 10. And we're going to put that into 8. What is it I'm really doing? I'm just putting 10 into register 8.
Yeah.
Next one, 0 and hexadecimal B, which is just 11. I OR that, 0 and 11, you get 11. I'm putting into 9. Then we're going to add contents of register 9 and register 8, which are, and when you add that, you get, oh man. All right, so it's not too early yet. And we're going to put that in register 10. I highly recommend you write exit, another label. It'll make more sense with these labels because it tells the assembler where you can jump to or move to. And when you went in your program, you do jump register, return address. That doesn't make much sense right now, but what's saying is, okay, exit the main function. And by exiting the main function, you are terminating your program. All right, let's go ahead and look at this inside of QT-SPIM. Nice thing about QT-SPIM is if you look right here, here's that OR I with putting 10 into register A, putting 11 into register 9, and here's the add. Now there's a bunch of stuff happening around, and why is that? Well, when your program loads, even on your computer, it has to do a lot of work. In fact, probably over 1 million cycles go by before your program's even started, because it has to do a lot of things to set stuff up. But for example, we'll just look at a couple of them. Notice up there, that first instruction is a load word, but over there it has something called argc. Does anyone remember? C, yes, argc, argv. There's actually a third one called environment pointer as well, but most of the time you probably haven't used that. And that's just setting it up. Then it's going to call main, which jumps down here and gets us started. All right, the nice thing about the simulator, it actually has lots of nice features.
Shows the registers.
Shows the registers over there. And apparently a bad feature is it won't let me resize it.
Great. It's okay. We can see.
Okay. But you can step instruction at a time. You could go simulator single step, or you just hit F10, which is what I'm going to do. I'm going to hit F10. Now we're up here on top, which means it's actually still setting up the function call to main. So I'm going to step through setting up of RV, the environment pointer. This is loading up the function call, and then jump in link is calling the function main. And now we're inside of main. So we're going to do $i $8. $8 is over here, which happens to be T0. It's your first temp. And we're going to OR the value of register 0, which is 0, and 10 into 8. So when I hit F10, watch what happens to register 8. Morning. It becomes A, which is 10. So what's going to happen with this instruction?
It's gonna put it into register 9.
What is it? 11. All right,
Or
good.
B.
B. Whoa.
I have to remember that.
Automatically.
I know, it's amazing. Okay, and now, what's this one going to do?
Register 10 gets 21.
21, which in hex, is it 15 in hex?
no
15 in hex. 1-5.
Oh, right.
All right, jump register. This is how you exit your main program. And so it's actually going to jump back to, after the jump in link, oops, up here, which goes to the no op. And then it's going to set up a system call with the load immediate, and then do the system call, which is exit, and that terminates the program. So this is what's really going on, a little more under the hood. All right.
Ta-da.
This makes some sense. We're going to go talk about more of the theory right now. All right. Good. Okay, let's see. IA32, I've been calling it x86, started in 78 with the 8086. We've been using it ever since. Intel has been trying to kill it, has tried to kill x86 on numerous occasions, and has failed each time.
I like to kill things.
Yeah. Oh well.
You know?
All right, transistors, 78, 29K, 82 at 134K. Yep, but nowadays we're up a million. Pentium 2 has more. Do we get the quad? All right, well, the i7 has about, I think it was 4 billion? That's a lot. A lot of transistors. So they're just more and more transistors going on. Core, wow, this slide needs to be updated. Last is Core 2 quad. Y'all remember that processor?
Nope.
Nope. All right.
Where'd you get this one from?
Underwood.
You don't remember those processes?
Yeah, you don't remember the Core 2 quad or Core 2 duo or Pentium D? Oh, the Pentium D.
I remember the Core 2 Duo.
There we go.
I think I had one.
There have been numerous companies that have tried to cut into Intel's market share of the x86, namely Cyrix, NextGen, and Transmeta. They're all dead. It's very expensive to try and enter this because Intel has billions of dollars to basically make you leave, and usually they will do so. The only one that has been able to compete is AMD, and the reason for that is, well, there's a long reason for that, but it's a long history. Intel originally did not make their own chips, so they had to contract it out, and one of the companies they used was AMD. And due to an error in the contract, AMD was allowed to print the chips that Intel made and sell them essentially as AMD chips instead. Haha. Whoops.
Smart.
Now, Intel caught on to that and made it so their new designs they couldn't just print and sell. But AMD took their old designs and started upgrading from there, and they basically had two paths competing against each other ever since. And it's gone back and forth. Oh yeah, maybe the slide isn't that old, 2017? So Ryzen's 7 chip to surpass the i7 in certain situations. So there's some good competition. And if you look out there, in general, AMD is cheaper than Intel. And right now it doesn't have the meltdown problem. Pentium Pro was one of the biggest jumps. Y'all probably don't remember that. Oh well. Basis for Pentium 2, Pentium 3, and I always want to call it the celery processor. But they call them Celeron. Pentium 4 is similar. Basically, they went from a standard single cycle that we're doing to a very wide issue where you could execute up to 5 instructions at once, and you can, well, pipeline it, which we'll get to later. All right, then the Itanium, known as the Itanic because it did not sell well, and then it died. This was Intel trying to kill x86, but no one wanted to do it. Okay, there's your history lesson. Any other questions about the history? I didn't think so. Ew. Okay, let's go ahead and start talking a little bit more about assembly and from the programmer's view, what's going on. So you're not coding in C, you're coding in something, a lower level language than C, which means you're actually writing the machine instructions that are going to be executed on your processor. From your point of view, you have access to your registers, you have access to condition codes, and this has to do more with branching and other things. I don't think we'll get into it too much during assembly, but there are condition codes. You know, did you just do a divide by 0? Oops. Are you branching? Was a branch taken, not taken? Stuff like that. And you can interact with memory. You send it an address, and then hopefully you can either get back data or you can send an address and data to what needs to be written to. And then also from memory, you're getting your instructions. You also have a stack, and this is the stack that we talked about in data structures. Let's see if everyone remembers what the stack was. Anyone? What is the stack?
Memory.
Memory? What was stored on the stack?
Objects and stuff. Addresses.
Local calls, function calls. Yeah, it dealt memory, yeah. Local variables, but mainly your function calls were on the stack. Your heap is somewhere else. We are not going to do the heap in assembly. That would take a while.
Let's not go back to that.
Oh, there's pointers.
No having to delete stuff.
You're right. No having to delete stuff,
That's nice.
but there are definitely pointers. There's no way to get around pointers when you do assembly. You have to have pointer. Well, how would you know what to execute where if you didn't have a pointer? It wouldn't make any sense.
We just don't code in that problem.
All right.
Back with the GCC.
Well, we're not doing GCC, but you need to understand how this fits in. In all actuality, when you use GCC, it did not assemble anything. All GCC did was take your C program and convert it to assembly. That's all it did.
Oh.
We're just going to bypass that step and just write the assembly. GCC would, for your convenience, automatically run the assembler afterwards to produce the binary. You might have program code, remember with your .O's that you created, and then you can link them all together to a final executable and then go ahead and run it. Okay. We don't need to talk about the linker. What's going on here? One moment, guys. Yeah, we're talking about this. Good. Here's a better example. Here's your C code for sum. Notice in assembly you have something called a label, and that is to tell the assembler where the sum function begins. And it's going to convert that to a memory address, which you'll use a pointer in order to find out where you need to jump to in the function. In here, we're just adding 2 arguments, A0 and A1 to a temporary, and then move that to the return register, which is V0, and then jump return to the return address. So this is what you'll be writing. This is how you do it inside of assembly, or not assembly, x86. Hopefully you can see by just looking at it, the first one's better than the second.
Yes.
It's a Y86.
Can't agree.
x86 has a built-in stack where you have to manually edit the stack via instructions. Here you just access memory and
Why
you
is it
call it.
labeled Y86?
That's the type of assembler, because there's different types of assembly notation, and this is the Y86 assembly notation. Good question. We're learning MIPS, or MIPS 2000. It's a reduced instruction set, so there's only few instructions as opposed to way too many. Not compatible with x86 because it's not x86. Why do we study it? It's easier, it's simpler, it's not ridiculous like x86. It also ends up being the way what x86 does anyways. What x86 does is it takes I'm just going to call it wacky instructions, and converts them to RISC instructions, namely the ones we have in MIPS. and then runs them anyways. So there's really just a level of indirection anyways to what's going on. We're not going to go into 64-bit, and we're not going to go into floating point. I take that route back. You are going to do floating point. But
Killing us.
it won't be that bad. Okay, label. This is to tell it of the memory address. And why, which can tell us what instruction to go to. You have regular instructions, commands. All right, direct. What is going on? Okay, we got lots of stuff. All right, let's go jump over to more examples.
Yay.
Thanks. All right. Everyone okay with this example? We're good? Okay.
Thanks.
Let's at least play with memory a little.
Okay.
Thanks. Thanks. Now we've added something to the data section. First off, we label it. Value is going to point to is the memory address of where the data begins. What?
I'm sorry. You just steadily were trying not to laugh when I did that.
Dot word. What does dot word mean, guys? Come on. You have to do this. Word. It's not Microsoft Word.
Dang it.
Aw. Only have
Those are
that
character values then, right?
Or is it
No.
string?
String.
No, that's not. This is not a string. String would be char,
Oh.
String would be
or
char.
ASCII, or actually it would be ASCII Z.
Yeah.
Okay.
Don't ask. Numbers.
Word. Okay, what? You got a byte is one.
Mm-hmm.
A byte is 1 byte. Okay, we're all good.
Yeah.
Okay, how many bytes are in a word?
Depends on the word.
No, it's
Four.
number of bits. Good guess though.
Wait, so bytes then would be 4.
4, right?
Oh,
So
I just
Yeah.
counted the letters.
I never realized that. All right, because
I
word
guess.
has 4 letters, therefore it has 4 bytes. That's terrible. But then
It
half
works.
word would be never mind.
It works.
So we're going to reserve 10 bytes. I'm sorry, 4 bytes. The first 4 bytes are going to contain the value 10. The 4 bytes afterwards are going to contain the value 20, and the 4 bytes after that are contain the value 0. So how many bytes are we reserving in total?
12.
All right. 3 numbers. Okay. So that's our data. That you can think of that as our global memory that we're going to use.
Woo.
Start the text section. Give the main label. Start the main label. Load address. Load the address value into temporary 0. What is value?
Something.
Good.
It's
something.
value.
It has a value. Correct.
It's
the
the
word
label's
right
an
there.
address
It's the address of
where that the labeled value
Oh,
is at.
where word is.
right. But
where it
which
starts.
which yes. So value is the address of where it starts. What does that sound like?
An array.
An array. And so namely we are using a
Pointer.
there we go.
Oh no.
See, we're not using the heap and we're already using a pointer. All right. Pointers are everywhere in assembly. Okay. So that's in T0. We're going to load from the address in T0 off, go over 0 bytes and take that value and put it in T1. So what value is going to be in T1? 10, because that's this guy right here. Then we're going to go load from T0 offset by 4 bytes into T2. So what value is going to be in T2?
20.
Okay, we're doing great. We're going to add T1, T2, put in T3. T3 now has 30. Wait, why was that one harder than the
Yeah, I
previous two?
remember which number.
What was added again? Okay. And now we're going, what does this last one do? Quick, someone tell me.
Store the word.
Okay, yes.
I guess
All right, so we got literacy
Read
down.
the instructions.
In other words than what I wrote up here.
It's going to replace that
Puts
0
it
there.
in memory.
All right, there we go. Replace that 0 with the value
The value
30.
So it's just 30.
How are we doing back there? I'm about ready to step through it in QT spin. We're doing good? All right. So let me go ahead and close that. We'll Qt, I don't know why I did fast start. Qt spim 02. That's the console. We don't need that. It's not gross. It's beautiful. All right. We'll get started. Again, we're setting up main. This will make more sense when we talk about functions. But let's go to our first instruction. So first instruction, load address T0 value. Notice that the actual instruction is load unsigned immediate, but we wrote LA. Load address is not actually an instruction in MIPS, but the assembler knows that load address is really just a call to load unsigned immediate, so it just does the translation for us. This is called a pseudo instruction because the load address doesn't actually exist, so it's not for real. But the assembler is able to easily translate that into what the real instruction is. You gave me the blank look.
I was just thinking for a second.
So value, well, this is the text tab. We can go over to the data tab, and here's where value is. It's this memory address. Notice the values afterwards is A, which is 10. 1.4 in hex is actually 20, and then there's the 0 afterwards. So we have the data over here, as well as a bunch of other data, but don't worry about that for now.
Why is there 4?
Why's what?
The 4.
What
Is
for?
that so you know where the stopping point? It has 0, and then it has 0 again, and then it has ++.
It's just showing you memory. It likes to give you, in case you are having memory errors and you're writing out of bounds, because this is really not going to tell you if there's a like null pointer exception or segment faults. Don't happen. It just goes.
Yes.
Yeah. Yeah.
Finally.
A lot of those.
All right. So if we're going to load value into T0, what value is going to be inside of T0?
One that's highlighted.
Oh, good. You took the hint. Yes. The value that's highlighted. So let's go back over here. We're going to execute this instruction. Number 8, which is T0, I execute it and now has the address. Notice that this address is that one right over there. All right, load word, $8, which is your temp. Notice again it translated from our instruction over here. This is why I like Qt spim, is it tells you what instruction you wrote and then the actual instruction that's being executed.
That's nice.
And then any comment you put on that line as well. It is nice. So T0, 0, offset 0 to T1. So if you notice, that'll pull that A over there. There's the A, and we'll go into this one as well because that's the 1.4 or the 20. Now we add the 2, put them into T3, 1E, and now here we are in the store word. We're going to store the value in register 11, which is 1E, into the beginning value of 8, address at 8, which is this guy, over offset. Go over to data, and I'm going to press F10 once, and notice what happens to that over there. And it goes ahead and stores it out. And we're now done, so we're going to do jump register to exit our main function, and no op, load or system call exit. We're done. All right. We're doing well? Okay. Let me pause the recording.